I am a visionary, exploring a universe of data to sharpen our view of the most distant galaxies, and studying black holes to help prove Einstein's theory of gravitational waves. I am a healer, giving doctors the power to turn mountains of data into life-saving breakthroughs, identifying diseases like leukemia from a simple drop of blood, even in our own homes, and finding new ways to bring cures to market faster. I am a protector, keeping our oceans safe from invasive species, and helping our crops flourish while minimizing pesticides. I am a helper, assisting customers in stores and the disabled in their homes. I am a navigator, mapping our world 1 millimeter at a time, and making even the largest self-driving vehicles safer for the long haul. I am a creator, learning to paint from the masters and applying their styles to create original works of art. I am a teacher, analyzing 500,000 player moves every game to identify strengths and weaknesses, and a learner, discovering new strategies from complex games. I am even the composer of the music you're hearing. I am AI, brought to life by Nvidia, deep learning, and brilliant minds everywhere.
Ladies and gentlemen, please welcome founder and CEO Nvidia, Jensen Huang.
Welcome to GTC 2017. Before I start, I just got to say, all of everything you've seen so far and everything you're about to see were all created by NVIDIA's creative organization. We have just an amazing team of creatives in our company. As you guys know, we work at the intersection of art, science, and engineering. And this intersection is what made all of this possible. I love the work that they do, the craftsmanship, the dedication, their absolute focus on excellence, their creativity, their willingness to take a risk, put themselves out there. And not only that, it was all done by themselves. And even the voiceover is done by one of our young employees, Helen Broinger, and her parents work at NVIDIA, and you know, we raised her, and that was her voice, and so I'm so happy about that. Her parents are going to be really proud. I've got a lot I want to talk to you about today. We have laws of physics, laws of computing. We have special guests. We have artificial intelligence, and so I've got a lot of stuff to cover, so let's get started. There are two dynamics that are happening in our industry at the same time. I'm going to talk about both of them. This is the first one. For the last 30 years, we have benefited from one of the most powerful technological revolutions that anybody's ever seen. The combination of two effects created what is known as Moore's Law. One, architectural innovation that makes microprocessors better and better, more and more performant through architectural techniques. The goal is to find instruction-level parallelism. And it's magic. Just think about what they're trying to do. Basically, a program is a sequential list of instructions, and it's performed one at a time. But somehow computer scientists have figured out ways to do them in parallel. Well, one of the ways that you do it is pipelining. To start the next instruction, to start the next step before the first step was complete. Make the instructions wider. Do all kinds of amazing things so that you could speculatively execute something in the event that maybe you didn't have to change course. All kinds of amazing technology was created. Caches got lots bigger, and then of course, software techniques on top of it, optimizing compilers, made it possible for us to advance microprocessor architecture performance year in and year out. And we deployed all those transistors to good use. Now, the transistors that we added, more and more and more transistors, wouldn't have been possible to use if it wasn't because of a second law, the law of Dennard scaling. Dennard scaling basically says that we can put more and more transistors into a constant area and run them faster and faster, so long as we continue to reduce its voltage, so long as we continue to make the transistor smaller, reducing its capacitance. And by doing so, the combination of these two factors, more and more transistors, running them faster and faster at a lower and lower voltage, allowed us to continue to advance performance within some constant energy envelope. In the course of the last 30 years, we've improved microprocessor performance by nearly 1 million times. By nearly 1 million times. Nothing in society has improved by 1 million times. And everything in society has been made possible because of this fundamental advance. Then in the last several years, it started to slow. Our abilities to harvest parallelism out of instructions, sequential instructions, started to diminish. And the number of transistors that we had to add in order to squeeze out that little tiny bit of extra performance was simply too costly. On the other hand, we were reducing voltage, shrinking transistors, and we're now up against the laws of semiconductor physics. There's only so far that we can push before Dennard scaling started to fail on us. We now have found ourselves at the end of two roads. And it's been incredibly well documented. We started talking about it, in fact, for many of you who've been coming to GTC all these years, I think I spoke about it at the first GTC. I speak about it at every GTC. And it's the reason of our existence. Recognizing that we need to find a path forward, life after Moore's Law. John Hennessy recently talked about it. He called it the end of the road for general purpose processors and the future of computing. Mark Horowitz, also a professor at Stanford, spent enormous amounts of time with his colleague, basically plotted out every single major event and processor product and node in the last 30 to 40 years. And the results are actually quite amazing. The blue line basically shows the Dennard scaling compounded with the lack of productive architectural innovations has led to the plateauing of processor performance. What used to grow at 50% per year, 50% per year compounded improvement is now improving at 10% per year. Yet, we can manufacture the transistors. The transistors are abundant. And in fact, if you look at it, look at that white line, that shows you how much transistors we have. And that was the ultimate observation of the beginning of our company. That observation was the reason why accelerated computing works. And it is the reason why we introduced the concept of GPU computing. GPU computing does several things. The first thing it does is recognizing the microprocessor is incredibly good at sequential instructions. It's incredibly good at single-threaded operation. That the craftsmanship and the innovation and all the engineering has gone into it over the course of the last 30, 40 years wasn't going to be replaced. And we respect the other law of computing, Amdahl's law, that if we were to accelerate the things that we could do, the part that we can't accelerate eventually becomes the problem. And so we have to make sure that we honor that law as we change the architecture of computing. We did several things. The first thing that we did was we realized there's some workload inside some very important applications, Frankly, these applications are the ones that the reasons why you are here. They're the algorithms of artists, of scientists, of engineers, of the explorers, the discoverers, the inventors, the Da Vinci's of our time, the Einsteins of our time. Their software includes some parallel computing aspects, some parallel processing aspects, that if we could figure out a way to offload of the microprocessor that was good at sequential processing, we could provide incredible speed up. So the first thing is to create a specialized, domain-specific accelerator that is a companion to the CPU, accelerated computing. The second thing we did was create an architecture that had a platform that we were willing to dedicate ourselves to everything we did for the rest of our lives. We created an architecture we call CUDA. And it's named after an architecture that we created in the very beginning of our company 25 years ago called UDA, Universal Driver Architecture. That architecture was extended for computing, Unified Driver Architecture, excuse me. That architecture was extended for computing starting 10 years ago. We call it CUDA. This architecture is our computing architecture. And a computing architecture that you dedicate your lives to, and you continue to promote, that you continue to sustain, you continue to improve, and it continues to add value, eventually, other people can benefit from it. It has to be special. It has to do something that general purpose computing, that commodity computing, or otherwise generally available computing cannot do. It has to be special. It has to be something you dedicate yourself into. It has to be something that is available everywhere. It can't just be available on a PC. It has to be available on a laptop. It has to be available in the cloud. It has to be available in embedded devices. It has to be available everywhere. It has to be thought about from top to bottom in the sense that you have to have tools. You have to have middleware because computer architects and computer scientists needs all of that to be productive. What's really special about GPU-accelerated computing was that it took enormous amounts of effort to port, to refactor for all of you the applications you've developed on top of microprocessors onto this new computing platform. It took time. And it took specialized skills. And so we dedicated ourselves to having a team of computational mathematicians that can think across the entire stack. So we work with you, work with the application makers, the algorithm developers, to find that match between the work that you want to do and the architecture we created. We worked at the architecture level, at the system software level, at the algorithm level, and then we worked at the application level. The reason for that is because if you want to overcome the limitations of Dennard scaling, you're going to have to do something pretty clever, and you have to think across every single possible layer of computing to find efficiencies, to get rid of waste, to do special and smart things. This way of doing computing, top to bottom, then bottom to top to bottom, then bottom to top, dedicated to one single architecture over the course of the last 10 years, the results have been phenomenal. If you look at the green line, that's basically the line that Nvidia is tracking. Some people have described our progress as Moore's Law squared. And the reason for that is because, first of all, you get a big speed up. You get a big speed up over the natural microprocessor performance. Secondarily, it appears to be moving faster than the rate of increase of transistors. And I think there's some logic to that. And the reason for that is exactly as I described, is because we thought across the entire stack. Well, for many of you who have been coming here for close to 10 years, I want to tell you how much I appreciate all of your support. We come here because the work that we do is impossible otherwise. The work that we do is impossible otherwise. The work that we do in creating virtual reality is impossible otherwise. The work that we do in computer graphics, the work that you do in fluid dynamics is impossible otherwise. In molecular dynamics, it's impossible otherwise. There are several regions, several domains that we have found accelerated computing to be incredibly effective. Of course, graphics, physics, quantum mechanics, and a new field called deep learning. GTC has been growing so fast. It has been growing incredibly fast since our very beginning. We now have increased by a factor of 3 in 5 years, the number of attendees. Now, the only reason why it hasn't grown faster is because of the fact that computing is all over the world. Since last year, starting last year, we've taken GTC on the road. Last year alone, over 20,000 people came to GTCs around the world. And this year, we're going to take this show on the road again so that we can make this computing platform available for developers, scientists, and researchers for your groundbreaking work all over the world. The number of GPU developers has increased by a factor of 10 in 5 years. It's actually amazing. 500,000 developers. It's taught all over the world. Textbooks are written all over the world. When you look in LinkedIn, you see CUDA all over the place. It's just fantastic. The number of people who now consider GPU or programming GPUs or programming CUDA, one of their specialties, is really fantastic to see. And then over 1 million CUDA downloads. The CUDA driver, the CUDA software SDK, has been downloaded over 1 million times. At GTC this year, every one of the top 15 technology companies in the world are here. 100% of the world's top 15 technology companies are here. 10 out of the world's top 10 car companies are here. Pfizer, Merck, and Roche, GSK, Amgen, Lilly are here. Researchers from the world's top 100 national laboratories are here. There are 80 AI startups here, 25 VR startups, all kinds of robotic startups and ideas. GTC is where, if you will, the future is invented. GTC is where we create what other people would think of as science fiction. And speaking of science fiction, my first demonstration for you today is the Holodeck. As you know, we play at the intersection of virtual reality and artificial intelligence. We play at the intersection, and nothing exemplifies that intersection like Holodeck does. And the Holodeck is not only a place you go, but it's a place we can share. And so it has to obey the laws of physics, otherwise it wouldn't feel like a place. It has to be photorealistic, and it has to be someplace that we can share together. And so I thought, gosh, what can we share together? What can we share together? And so I thought it would be great to invite a friend to join us from Sweden. And he's actually a pretty special guy. His name is Christian Koenigsegg. Do you guys know Christian Koenigsegg? Christian Koenigsegg is a car maker. Not a normal car maker,
left hand.
a hyper car maker. And that's a description of him, not the car. Come on. Guys, help me out here. That was incredibly fast, thinking on my feet. There are many more jokes to come, watch. Some of it is just gonna be right in here. It's incredible. And so I invited Koenigsegg to come and show us something that most people have never seen, and to enjoy the Koenigsegg Regera. Ladies and gentlemen, let's go into the Holodeck. Hey guys, hey Christian, which one are you? Christian?
Just stepped out. He'll be right back.
He went to the bathroom?
Got away?
Hi, Christian.
Hey Christian, could you scratch your head so we know which one you are? Everybody was waving. All right. Okay, so this is Nvidia's Holodeck. We have people in it from all over the world, and The thing that's really, I think is just incredibly cute that they're all wearing name tags so they know who each other. That's very funny. Okay, so why don't you guys take us through? Let's see the brand new Koenigsegg, shall we? You guys know this is how the holodeck works. This is all completely in real time. This is photorealistic graphics. This is why it's so fun to work at Nvidia. Man, oh man. Hey, so Christian, what do you think about the car? Tell us about the car. Christian?
Yeah.
Can you hear him?
No? What happened? Put on your headset.
Okay.
All right. It's a telephone. You can use this. Okay, Christian, are you there? Wow.
Yeah. Well, can you hear me now, Justin?
Well, don't breathe like Darth Vader. Okay, so Christian, first of all, tell us about your car. So this car is a hypercar. It's a V8 twin turbo with 3 electric motors in it, right? So take it from there.
Yeah. So this is our latest creation. It's a hybrid car with direct drive, no gears. We have a combustion engine with up to 1,200 horsepower, and then 680 horsepower of electric drive. So this car doesn't need any gears to go from 0 to 250 miles per hour in only 20 seconds. It's really one of the absolute fastest cars ever produced for road use, and something I'm very proud of. And seeing it in this environment is just amazing. Trying out this system with you guys really changes the view of what's possible, how to create the cars and showcase them during the building process. It's just fantastic.
Now, Christian, you know that the first time you sold me a Koenigsegg, it wasn't even street legal.
You're right. It was in California. It was street legal in the rest of the U.S., but
Yeah, whatever.
Correct.
Whatever. And so I just want to let you know I drove it anyways. And the thing that was really great is that whenever I get stopped, it's never by a police. It's usually by an old lady who would like to take a picture of her grandson in the car. But I had the perfect excuse. I was going to say that if I got stopped, I'm taking the car to the showroom, and apparently that was going to work because you told me that would work. And that it was okay to drive an illegal car. All right, so let's take a look at this. Everything here is carbon fiber. Let's go inside it. Let's go inside it. Let's take a look.
Amanda, please.
Amanda, let's take a look.
All right.
And remember, everything obeys the laws of physics. So if she were to grab the steering wheel, her hands don't go through it. Wow. Look at that. Look at that. Oh, look at that. Okay, all right. All right, come on out. Don't you guys have an X-ray feature or something like that so that we could see through the car? I mean, I just wanted to make sure that the entire car design is there. Every single body part is in here. This is not just a video game car. This is actually a computer-aided design car. This database came directly from Christian, and now that we have his database, we can 3D print it ourselves. Look at that. Isn't that amazing? But what if I want to see like all the parts? I just want to do an inventory of the parts. Okay, you guys, thank you. Thank you very much. All right, enough fun. Ladies and gentlemen, Christian Koenigsegg, the Holodeck. The Holodeck. It is just so amazing to be in these environments together with all your colleagues, and you're talking to each other, and you're pointing at the same thing, and because you could touch things, you could actually lift things up. And because you're in that environment and you're superhuman, it reacts to physics, but you can lift up amazing things. And so the holodeck is such a great place. The first dynamic is the emergence, the rise of GPU computing. The second thing that happened several years ago. And in fact, some would call this the second era, not of processing, but the second era of computing altogether. As you know, when you guys are doing a search on Google, somehow it magically knows what kind of information you're interested in. When you're watching movies on Netflix, somehow it magically knows what are other movies that you would enjoy. And when you're shopping on Amazon, it's amazing that every single page is personalized for you. And that it knows, based on the type of shopping habits that you have, there are other things that you might be interested in. None of those programs were written as a sequence of instructions specifically by engineers. All of that was made possible by machine learning. It's learning from all of your behavior and all your interactions with that service, and over time, it becomes more and more predictive. It is almost able to anticipate your needs. Machine learning is one of the most important computer revolutions ever. Whereas computer scientists used to specify every single instruction a line at a time, now algorithms write algorithms. Software writes software. Computers are learning by themselves. Machine learning, the era of machine learning. Pedro Domingos, the University of Washington professor, wrote a really elegant book, and it's called The Master Algorithm. And he describes that there are 5 tribes in machine learning. The symbolists, people who use inverse deduction, induction. The Bayesians, probabilistic inference. The analogizers, the evolutionists, the ones that believe in genetic programming. These 4 approaches are also making enormous contributions in computer science. But one particular tribe called the connectionists have recently bursted into the public consciousness. This particular approach, which is now called deep learning, is the culmination of research breakthroughs from so many different labs, from Schmidhuber's Swiss AI lab on using GPUs for convolutional neural nets and the early uses of LSTM, long short-term memory, recurrent neural nets, to Jan LeCun's work with CNNs, to the groundbreaking invention of backpropagation by Jeff Hinton at the University of Toronto, the work that Fei has done on ImageNet and computer vision at Stanford, and of course, quite famous work by Andrew Ng on deep learning at Stanford as well. All of their works have come together into, if you will, kind of called the Big Bang of deep learning, the Big Bang of modern AI. And Fei gave a talk recently where she was talking about the search for intelligence. And she said that the Big Bang of AI, what made it possible were 3 fundamental ingredients. The breakthrough of deep learning was made possible by 3 things. Of course, the culmination of all of those great ideas that came together into the deep learning algorithm and the deep learning approach. The second is the availability of an enormous amount of data. And third is the discovery of using GPUs to accelerate deep learning, the training of deep learning, the development of the network, the model. Well, that combination set off in 2012 one of the most amazing progress in computer science. That culmination, that Big Bang, allows computers to magically look at an image, determine what's the important features, learn the features hierarchically, from pixels to curves to objects, for example, my face, my ear, my nose, my eyes, to eventually turn it into a face, and my face. That it learned it hierarchically and was able to represent knowledge, represent information in this way by extracting it out of raw data all by itself. It is able to look at a picture of me and recognize that it is me. It is not only robust, it is diverse. It could recognize me in the sun, in the dark, with a hat on, half of my face occluded in shadow, maybe slightly turned away. It could recognize other people. It can generalize. The ability for these networks to not only be robust and diverse and generalize allows us to solve one of the great challenges of computer science up to this point, which is perception. Sensing the real world, sensing raw data, whether it's visual or audio or otherwise. It could be vibration, it could be tremors, it could be temperature, it could be access to your data storage in your corporate storage. And all of a sudden, boom, by solving this problem, we just went on a massive race since 2012. One breakthrough after another was made possible because of it. Self-driving cars, the ability, Baidu using computer vision, translating it to text, Google self-tagging all the photographs that you upload. You no longer have to tell it where this picture was taken. It figures it out. You could ask it for all of your pictures of beaches, and it'll find it for you. For the very first time, a deep learning network that was trained by data, not coded by engineers, not coded by computer scientists, was FDA approved for medical imaging, cardiac medical imaging. And it just keeps on going. Recurrent neural nets came along. The ability for neurons, these networks, to learn time sequence information so that it can understand sequences of text that turns into words, sequence of words that turns into paragraphs. All of a sudden, we have speech recognition that are superhuman. We have the ability to now look at a video and caption it automatically. So this piece of software has learned what is in the video and what it means. Captioning. Another architecture came along called reinforcement learning, where the network is given a value system and it tries and tries and tries and tries again exhaustively until it figures out how to improve itself towards the value system. Reinforcement learning. How we learned to just about do everything. As a result of that, one network called AlphaGo was able to beat the world's champion in Go called AlphaGo, and it was a feat that nobody thought would be possible for another 20 years. Robots are learning how to translate computer vision sight to kinematics, hand-eye coordination, and it keeps on going. And now we have unsupervised learning. We have the ability to use autoencoders to enhance images, to fill in the missing spots. And then a breakthrough came along this last year, or I guess Ian Goodfellow's paper was 2014, but this last couple of years, it's really taken off. Adversarial networks, training two networks at the same time. One network's job is to fool the second network, and the second network's job is to not be fooled. And so it's a little bit like one network learning how to be Picasso and generating images and paintings of Picasso, while the second network is learning how to discriminate whether it is truly Picasso or not. When you're done training this network, what you end up with is a network that is able to draw like Picasso, and you have another network that is able to recognize images and recognize paintings at a level of discrimination unheard of. Generative adversarial networks. As a result, all of a sudden, all of these new ideas for generation comes along. We could we create things like style transfers, generating voice, the ability to fill in empty spots or missing spots in photographs, natural language translation, to go from one language to another language, and to learn a pair of languages and then transfer that learning to other pairs of languages. So you learn how to translate from German to Spanish, and all of a sudden you're able to learn how to translate from English to Spanish equally well. Zero-shot learning, transfer learning. These just spotlight a few of the examples. The number of papers in deep learning is just absolutely explosive. There's no way to keep up, and it's literally everywhere in the world. That big bang, that second dynamic of computing, the big bang of deep learning has really laid the foundation of what we now all know is the coming era of artificial intelligence, where computers are now able to automate programs. Automation of automation. Computers that program computers. Artificial intelligence. Let me give you an example of something that we've been working on. We also, in our company, we do a fair amount of deep learning research. Let me give you an example of what's actually happening here. Basically, this network in the middle, this is just an articulation of the network, it's called an autoencoder. We're asking this network, if we gave it a distorted image of that, a noisy image of that it has to learn how to generate that image, the beautiful image, from that noisy image. The way that it has to do that, it has to figure out how to recognize the important features and eventually generate it automatically. Now, one of the areas we've applied this to is ray tracing. Ray tracing, as you know, is computationally incredibly intensive. Following photons around as we try to regenerate an image is very computationally intensive. And so one of the things that we decided to do is what happens if we were to teach a network to fill in the spots that we haven't rendered yet, okay? To generate some of it and to automatically infer or to use artificial intelligence to decide what to fill it in with. And so let's take a look at that. This is our ray tracer with deep learning. On the left, let's see. On the left here is without deep learning. On the right is with deep learning. Notice how noisy it remains for some time. With deep learning, it figured out, based on the surrounding things that it has already rendered, and based on recognizing what objects look like, what paint looks like, what glass looks like, it's learned those things, and it's selected the right selected the right colors to fill it in with, all by itself. And as a result, you're able to take this noisy image and turn it into a beautiful image. Isn't that amazing? The implication is actually quite amazing. We can now get distorted input from the sky, from the internet, and somehow we could have a network running here that regenerates what it's likely to be. Okay, autoencoders, using deep learning for computer graphics. That's great, thanks guys. Now this particular image, let's take a look at this. This is the full scene, yeah, let me not forget this. This is now the full scene. Now let's do the ultimate stunt, let's go outside. And just like that, it fills it in. And it recognizes that it's a reflection of trees. And it renders a reflection of trees. Okay? Fantastic, thank you. Using deep learning for ray tracing. The AI revolution is well on its way. It started with the Big Bang in 2012, but since then it has grown incredibly. There's just amazing things that are happening. If you take a look at the major conferences, NIPS, ICML, CVPR, and ICLR, the attendees has doubled in 2 years. It's only doubled in 2 years because there are limitations in physical space. The number of students who want to learn deep learning has 10x'd in 2 years on Udacity. The number one most popular course on Stanford, at Stanford, is CS 229, Introduction to Machine Learning. The most popular course, you would have thought home ec was, but the most popular course is not being a movie critic anymore. It's machine learning. And in fact, I understand that it's not just engineers, not computer scientists, but it's psychologists, it's biologists, it's oceanographers, it's basically everybody. Deep learning has democratized computing. Not everybody knows how to program, but everybody has data. Everybody has their own data. And they could use that data now, use the experience of their domain, the experience of their career, the experience of their professions, and teach a computer how to automate their work. So teaching computers is something that I think everybody can do. We have democratized computing. And then lastly, the number of startups have been explosive. They're now 10 times as much investment in AI companies since 4 years ago. There's no question we're seeing explosive growth. Our strategy here at Nvidia is to, number one, create the most productive platform for deep learning. It starts with, of course, building great GPUs, but building great systems and system softwares and all the middleware that goes with it. The invention of cuDNN so that we containerized, we turned into a library the really complicated numerics and mathematical processing of all of the layers, the convolution layers, the activation layers, the pooling layers, all of those complicated layers into an easy-to-use library has been completely revolutionary. We've kept on going. There's all kinds of libraries that we've created now for the Deep Learning SDK that's available to framework designers and deep learning engineers all over the world. We work with every single one of the framework providers in the world. We have engineers that are working with each and every one of them so that we can integrate and optimize and make as wonderful as possible and as productive as possible these complicated frameworks, which are basically high-performance computing software stacks to run on NVIDIA GPUs. Every single framework on the planet supports CUDA. Every single framework on the planet supports NVIDIA GPUs, and it doesn't matter which one you use. Some of them have their own special characteristics. Some of them are better for research. Some of them are better for production. Some of them are better for cloud. Some of them are better for enterprise. Some of them are better for the highest possible performance. Some of them are better for flexibility. There are so many different frameworks, and we support them all. We also work with the system companies to make sure that irrespective of how you would like to access a high-performance computer, whether you would like to build it yourself by going to the store and buying yourself a GeForce Titan X, or buying a fully integrated server from one of the world's large OEMs, our partners HP, Dell, and IBM, Cisco, and Lenovo, or you would like to provision it in the cloud. One of the best ways to enjoy deep learning is for someone else to build this incredibly complicated supercomputer on your behalf. And so we've worked with all of the cloud providers, and at this point, every single cloud company in the world has NVIDIA GPUs provisioned in the cloud. And so with this strategy, we have accelerated the capability of deep learning, made it compatible with literally every single framework on the planet, and made it available to you however you would like to access it. But we didn't stop there. There's several things that we're doing. Because we realize what an important computing revolution this is, and that we can't just make the computers for it, that we have to understand how deep learning works and how AI will impact society, Bill Dally and our NVIDIA research is doing basic research in deep learning. We also have applied research. I showed you one example of our applied research. We're doing applied research in a whole bunch of areas. I'll talk about some of them today. We also partner with the world's top AI laboratories, whether it's University of Toronto or Stanford or Berkeley or Oxford or Harvard or MIT or Tsinghua University or the University of Tokyo. We have some 20-some-odd universities that we're working with around the world where the greatest, the brightest minds in artificial intelligence are supported and working directly with us so that we can advance the future of computing together. We also have dedicated teams that are working with each one of the vertical industries. I already mentioned the number of healthcare companies that are here. We work with enterprise, we work with internet service providers, so that we can make this computing platform available to all. One of the most important programs that we have in the company is called Inception. And many of you in the audience are part of this program. There are 1,300 startups that we're working with today that are focused on deep learning. You need early access to technology. You need access to resources. You need access maybe to expertise. You need access to market exposure. Sometimes you need access to funding. We have access, and we provide all of that as part of Inception. 1,300 companies came out of nowhere. This program is literally 18 months old. There are all kinds of great companies here. Deep Genomics in healthcare, Zebra in healthcare, medical imaging. We have financial services, fintech. We have retail and e-tail. There's autonomous machines, amazing, cool autonomous machines. We only talk about self-driving cars a lot. Zoox has a self-driving taxi that they're building. There's Drive AI, who's building a software stack on top of Drive PX. Amazing companies out there. Blue River is using autonomous machines to make it easier for farmers to fertilize their fields. One particular company that I want to mention that's really, really cool, and it's a company that is, in fact, now working on deep learning. It's just the technology that they create is so vital to almost everybody who's working in big data. And it's a company called MapD. Todd Mostek's company was the world's first to create basically a database engine on top of GPUs. And he's been working on this for quite a few years, and he just recently open sourced MapD. You should all take a look at it. It's just completely amazing to be able to access databases so large, completely in memory, and be able to interact with it, create graphs out of it, query it with AI, visualize it, all in real time. Completely revolutionary stuff. So 1,300 startups in Inception, and we're just delighted and really, really proud of all of them. Let's give them a round of applause. Deep learning in enterprise. SAP is one of the world's largest enterprise software companies. And recently, they reached out to us and wanted to partner with us on deep learning, and our two engineering teams have been working together on a new product that is just super, super cool. It's called Brand Impact. And the way that this works is this. There are videos being shown by advertisers, and they spend some $60 billion a year advertising their brands and advertising products, but they really have no idea how effective they are. So let me run this video for you, and you get a sense for it.
SAP Brand Impact is a fully automated and scalable video analytics service for brands, media agencies, and media production companies. Detected brand assets are framed in the video and correspond to the lines in the panel below. It allows interactive review of original video footage overlaid with detections. In the summary view, you get reports on brand exposure duration and size on the screen. In the detailed view, you get indication of each brand's screen coverage and frequency of exposure graph. SAP Brand Impact solution, accelerated by Nvidia, enables customers to measure the impact of brand exposure on their business performance.
It makes so much sense. It makes so much sense for SAP to be working on deep learning, and the reason for that is this. You guys know that some 80% of the world's commerce flows through the SAP ERP system. Almost 90% of the world's largest enterprises have their databases all within the SAP ERP system. So they're sitting on a pile of data. Companies who are using SAP are sitting on a pile of data. If we could figure out a way to use AI so that we could harvest, so that we could find insight in that dark matter, it would be incredibly valuable. It's one of the reasons why we partnered up with SAP and the results. This is the first results of it, and you're going to see a lot more to come. Well, there's so many different startups that are emerging all over the world. But the part of it that's really, so you're seeing startups that are emerging, number of applications is exploding, the number of industries that are being touched by this, and simultaneously, the complexity of the models are exploding. It means this is Microsoft's ResNet, the groundbreaking work that achieves superhuman levels, has 7 sextillion operations, 7 exaflops. Okay, 7 exaflops. Just to give you a sense, if you took all of the world's fastest supercomputers, all top 500 of them, you put them all together, and if you could figure out a way to cause them to operate for 1 second together, that is 1 exaflops. So what this network, this model that Microsoft created, called the ResNet, really, really super deep, the deepest network at the time, it would take 7 seconds for every single supercomputer on the planet, all the ones in the United States, all the ones in China, all the ones in Europe, you gang them all together, it would take 7 seconds to process this network. Okay, that's how much operation is inside. Very few of us think about the word sextillion every day. These are big numbers. These are a whole bunch of numbers, and that is what a program looks like in the future. Well, the program is getting larger and larger. Baidu has a network, a model that's 20 exaflops large with 300 million numbers inside it. And that's called Deep Speech 2. And Google's recent neural machine translator that does multi-language translation requires 105 exaflops. The amount of computation necessary is just incredible. In fact, it would take approximately one server, one CPU-only server, 2 years to run through this network one time. This is the ultimate high-performance computing problem. And that's one of the reasons why we have to continue to push the living daylights out of computing. Ladies and gentlemen, I would like to introduce you now to the next chapter of computing, the next level of computing. I would like to introduce you to something that has taken several thousand engineers, several years to create. It is a masterpiece on many levels. It is the most complex project that has ever been undertaken. Arguably the most expensive computer project the world's ever done. Ladies and gentlemen, the Tesla V100. This is made out of TSMC's 12 nanometer FinFET, and I'm just getting a little exercise up here. 12 nanometer FinFET. The part that is really shocking is this is reticle limits. Reticle limits basically means that it is at the limits of photolithography, meaning you can't make a chip any bigger than this because the transistors would fall on the ground. Every single transistor that is possible to make by today's physics was crammed into this processor. 21 billion processors, almost 100 billion vias, little connectors, 100 billion vias. To make one chip work per 12-inch wafer, I would characterize it as unlikely. And so the fact that this is manufacturable is great. It's just an incredible feat. 800 millimeters squared. If you guys have an Apple Watch on your wrist, the die size is approximately like that. Okay, so just take a look at your Apple Watch, gives you a feeling for it. 5,000 processor cores in here, 7.5 teraflops of 64-bit floating point, 15 teraflops of 32-bit floating point, and a brand new type of processor. A brand new type of processor called Tensor Core, which results in 120 teraflops of tensor operations. 120 teraflops. Unbelievable. This, well, the R&D budget is approximately $3 billion, and this is the first one. So if anyone would like to buy this, it's $3 billion. I'll just stick that in my pocket. The memory system in our architecture is quite unique. If you take a look at the way that most processors are organized, the register files are very small, the caches are very big, and the DRAM is quite large. In our case, the register file is huge, 20 megabytes of RF register file, so that the memory is very, very close to the processors, and that's one of the reasons why the throughput is so high. 16 megabytes of cache, and we're utilizing the state-of-the-art, the fastest memories that the world can make today. It's made by Samsung. Our partnership with them is terrific. The two engineering teams have been working so closely together, pushing the limits of how fast we can drive memories. And we've been able to achieve 900 gigabytes per second. It is just so fast. And then lastly, the second generation NVLink gives us 300 gigabytes per second, basically approximately 10 times the fastest PCI Express in the world today. Ladies and gentlemen, the Tesla V100. The Tesla V100, Volta has a new instruction inside. It's called the Tensor Core. It's a new CUDA tensor operation instruction that is both an instruction as well as data format. It's a 4x4 matrix processing array. And it basically does one of the most important primitives of deep learning, A times B plus C on a matrix. A times B plus C on a matrix. And so the input is A matrix, 4x4, 16-bit floating point, times B, 16-bit floating point, plus C. And we're trying to do that as fast as possible. So this is the way Pascal did it. And it did it incredibly fast at the time. And the reason why it's incredibly fast, every single row is multiplied by every single row is multiplied by every single column, and then when you're done, it accumulates, adds it all the way vertically into that green, the output results. And it does it incredibly fast because Pascal has thousands of processors. Because Pascal is doing this thousands of times at the same time. And that's the reason why Pascal was so fast. However, we felt that that just wasn't fast enough. What we should do is do it in parallel and in parallel. And so this is what the Volta Tensor Core does. It literally does the 4x4 multiply plus C at the same time. And it dumps it into result, 20 times increased throughput. Really crazy stuff. The net result is, although Pascal, the P100, is the most advanced processor the world's ever built, 1 year later, Volta is 1.5 times the floating point performance general purpose computing, 12 times the tensor operations compared to Pascal for deep learning training, and 6 times for inferencing. I'm going to come back to inferencing a little bit. Inferencing, for all of you who are not familiar, training the network is the first step. Very computationally intensive. And the second step, also computationally intensive, not as intensive, but computationally intensive, is inferencing, the production, the application of the network. Well, that's Volta, that's V100. And let's go through a couple of quick demos. You know, you guys know that it's a GPU, so although I haven't spoken much about graphics, it is able to do graphics. And so 10 days ago, I reached out to Tabata-san. Tabata-san is the head of the studio at Square Enix. And this is, as you know, the 30 years of Square, and they're well known around the world for the incredible cinematic production value of their films and video games. And with this generation, with Final Fantasy 15, his vision, Tabata-san's vision, was to unify the pipeline, unify the workflow, unify the graphics engine of cinematic film and real-time computer graphics, with a vision that someday cinematic film and computer graphics have essentially the same visual effects. And so 10 days ago, I reached out to Tabata-san. I asked him if he could do something for all of you. And he just jumped on the opportunity. First of all, he apologized. He said, look, there's not enough time to really do anything at the level that Square would like to do. However, he dedicated his engineers. They worked around the clock. They basically haven't gone to sleep for 10 days. And let's take a look at the great gift that Tabata-san and the Square Enix guys have done for us. Fur simulators, leather simulators. The amount of geometry in here, the lighting system, the soft shadows. The character is directly out of the movie. Metal looks like metal. You could almost touch the leather. That's a good leather jacket. Guys, that's a good leather jacket. I just noticed that. That's a good leather. I'm going to have to call it Tabata-san. Okay, good job, amazing. And so he also sent us what he believes that it will look like someday in the near future, and this is what video games will look like. Ladies and gentlemen, a quick trailer. Kingsclave. That's how I want my video game to look. This engine is called the Luminous engine. It incorporates 100% of all the physics processing that we've developed in GameWorks and all the particle systems you saw, the explosions, the fire, all of the destruction. So beautiful. All made possible because of NVIDIA physics engine. Well, let's look at something new. Several years ago, when we announced Kepler, which was a groundbreaking GPU, it was our first double precision GPU. It is the GPU that ended up in our nation's fastest supercomputer, the Oak Ridge Titan. It is the namesake of the GeForce Titan X, as in the fastest supercomputer in our nation, the fastest supercomputer you can build for yourself, the Titan X. Several years ago, we demonstrated Kepler simulating the future of our world. You know, people always look at the past of our world. By looking at all the images from the sky, and we could learn about how our universe was created and formed, but very few people really think about how our universe is going to turn out. Well, in order to figure out how our universe is going to turn out, we have astrophysicists in our company. As I mentioned earlier, one of the things that we're super proud of is we have computer vision experts. We have astrophysicists. We have quantum chemists. We have all of these, we have molecular biologists. We have people who are expert in these computational sciences so that we can work with all of you to advance your work. And so, ladies and gentlemen, Stephen Jones is going to give us what the galaxy looks like billions of years from now.
Okay,
Stephen?
so it looked like a piece of artwork, but that is actually a live simulation. We're showing an n-body simulation code here, courtesy of Jeroen Bedorf and Simon Portegies-Zwart of Leiden Observatory. And this is a simulation of the Andromeda Galaxy on the right-hand side, and it's
Hey, Stephen, wait. I need your demo to last less than 1 billion years.
All right, let's get going with it.
I've got a few. It's
All
not
right.
moving.
So we'll start. So
Yeah,
we're following
let it
the
run.
Andromeda here, and it's flying in towards the Milky Way. And in 5 billion years, about 4 billion years, it's going to make a close pass. It's going to swing past us, and it's going to start spinning stars off the Milky Way and the Andromeda. But gravity is going to inevitably take over. And what you can see, we're running this on Volta, and the number of stars, we can simulate 100 million bodies per second. We can see the bar structure of the Milky Way right there, right next to us, as it comes plunging back for its second pass towards the core of the Andromeda Galaxy. And then the cores get much closer, and you start seeing stars being flung off to all sides. One of the amazing things is you can look out into the universe, and you can see galaxies colliding in just this way, and you see the same kinds of structures as see these stars being thrown off in waves as the cores orbit each other and then finally merge. And so about 5.3 billion years, you can see the timer in the corner there, the merge is finally, this is it, this is the moment when all the stars get thrown away, and we get left with one single giant galaxy, the fusion of the two, with a whole pile of stars, probably including our sun, unfortunately, just flung out into the universe.
All right, thank you. All right, so the amazing thing about that demonstration, before I go into the next one, the amazing thing about that demonstration is this. 5 years ago, when we showed it to you on Kepler versus today, basically was 7 to 8 times performance improvement in 5 years. 7 to 8 times improvement in 5 years. So if you say 7 to 8 times performance in 5 years, and during that same time, the microprocessor has improved in performance by about 50%. Okay, 50%. Another way to think about it is 7 to 8 times in 5 years is basically about 70% per year. The benefits of accelerated computing. Okay, so one of the really important, and only at Nvidia would engineers love so much watching galaxies make love. That's science porn right there, brother. Thank you, Stephen. Thanks, everybody. That was incredible work. This is beautiful. Okay, now let's talk about deep learning. So recently, Cornell did a paper that was really amazing. So what they were able to do is, you guys know that it's now possible to take two pieces of art, learn the style of Picasso or Monet or Van Gogh, and you could apply it to a photograph, and it turns your photograph into a Monet. Okay, turns your photograph into a Monet. It's called style transfer. Well, the Cornell team, Dr. Bala's team, realized that what is left behind is artistic, meaning that it's distorted. The photograph is now distorted. It no longer retains its original fidelity. It doesn't look like what it used to look like. The buildings don't look like buildings anymore. They kind of look like buildings. It applies art to cats and dogs and grass. And so what they would like to do is photographic style transfer. You learn the style from one photograph, and you apply it to another photograph. You learn the style from one photograph, you apply it to another photograph. Basically, the way it works, well, you know what I'm going to do is I'm going to kick it off. Julie, Demarais, please. Did I say it right? Demarais. Demarais. I said that so that Madison could hear it. She's in France, and she's going to Demarais. Demarais. Yeah, that means to start, all of you. Okay, all right, so go. Do I have to click? All right, Julie. Démarrer, s'il vous plaît. Julie is one of our deep learning computer scientists, and she speaks French. And she was a professor, and so she is going to learn English so she could communicate with me, and I'm going to learn French so I can understand her. And we're going to use transfer learning to achieve that. So one photograph, this is the first photograph, we're going to learn the style of that. Okay, next, please, keep on going. And we're going to try to apply it to this one. Now, the thing that it has to understand is it has to understand the structure as well as the style. It has to understand the structure as well as the style, because it needs to apply the right style to the right areas of the photograph. And so it needs to understand a building's a building, a cat's a cat, water's water, the walkway's a walkway, the clouds are clouds, and when it applies it, it generates it. It's drawing the pixels one at a time, regenerating the photograph in this new style. And when the Cornell engineers wrote the paper, they used the Titan X to do that, and it took 3 to 4 minutes to process this image. This is now on Volta. Go ahead, fire it away. And so it starts out, here's this artificial intelligence network. It's trying to draw this image. It's trying to generate this image from scratch. It took this style and this image, and it says, I want to recreate something that is photographic. And notice the beach looks like the beach. The clouds still look like clouds. And somehow the style of that image has now been applied to this image. Pretty great. Thank you. Au revoir. Inserting that French in my mind just made me lose my track. We're in trouble. Okay, so deep learning style transfer. Now, what was possible on Titan X in several minutes is now possible in a few seconds, and you can now kind of get a sense for what deep learning can do, what the artificial intelligence network is able to do. It's able to generate an image based on what you teach it. Now, it didn't just learn from these two images. It had to learn structure from lots and lots of images. It had to understand what are important features from lots and lots of images. And after it's done learning all of that, you could give it 2 new images and say, I want you to take this structure, this image, and apply the art, the style, to this image. And it just does it all by itself. The performance of deep learning is everything. Cafe 2 is a framework that we worked on with the team at Facebook, and recently they announced that Cafe 2 is now going to be Volta ready. It's really delightful to work with them, and our engineers are working really closely together. These frameworks are incredibly complicated. We worked also with Microsoft on their cognitive toolkit. One of the things that's really great about the Microsoft toolkit is that it's able to scale incredibly well. Let me show you the numbers. If you look at Cafe 2, the Kepler performance, 8 supercomputing GPUs, was able to train this network in 40-something hours, basically almost 2 days, Last year, with Pascal, you can get a DGX1 box, and you can train that same network basically within a day. And now with Volta and P100, you can train that network in a shift. The productivity of these engineers is so vital, and the reason for that is because there's so few of these amazing deep learning scientists, and their time is scarce. The productivity of deep learning, the magic of deep learning is so great that everybody wants to jump on this and get products to market. And so the pressure on all of these engineers and scientists to deliver is incredible. That's one of the reasons why there's so many acquisitions happening all over the world. Now, when you finally get those engineers, you want to make sure that they have the best possible technology, the most productive environment to develop their network on. So the difference between having to wait for 2 days versus literally one shift is groundbreaking, but you want more than that. And so Microsoft's cognitive toolkit, what used to be called CNTK, can now train a network, multi-node training of the ResNet 50 network, which is a really gigantic network, and it integrates our SDK called Nickel, collective communications, basically allowing all of the GPUs to work together as one big farm. They are able to scale 64 Voltas together and turn what used to be days, hours, shifts, down to basically a couple of hours. So with 64 Voltas behind that deep learning scientist, now the iteration could happen much, much more quickly. One of the newest networks is called MXNet. Incredibly popular, and it's come out of nowhere, and it's growing like a weed. Everybody loves it because it's so scalable, it's flexible, and we're working with Amazon to enhance it for Volta. And recently they benchmarked it on Volta, and using LSTM, which is a network for time sequence learning, we're able to improve the performance dramatically from previous years. And so now we can train on one GPU alone, MXNet could be trained in just several hours. To come and share some of their insight about the work that they're doing in artificial intelligence, we have a special guest with us today. This is Matt Wood, the General Manager of Artificial Intelligence for Amazon. We're so happy to have you come and join me on stage here. Hey, Matt.
Good morning.
Welcome.
Hey, Jensen, how you doing?
Great to have you.
Hey.
So first of all, I think that everybody knows about Amazon's artificial intelligence effort, even though you guys have been working on it for so long. They really, really learned about it because of Echo and Alexa.
Yeah, I mean, we have been working with machine learning and deep learning for over 20 years at Amazon, and it's become one of the arrows in our quiver, really across the organization, from fulfillment all the way through to the work we're doing in taking this magical technology and giving it to all developers through AWS, through defining entirely new categories of products and experiences like Echo, Echo Look, and Amazon Go.
Yeah, one of my first recollections of Amazon was when Jeff said that he was going to have millions of books in the store. And I still remember the book company, the traditional book company said, oh, there's no way you could have 2 million books in the store because who's going to go through 2 million books? Well, the reason for that is because they didn't understand machine learning.
That's right, and one of our very, very early usage of machine learning was in driving discovery and search on our retail site. So the famous customers who bought this also bought is all driven through machine learning, and that's really now used extensively across the site for search, discovery, summarization, you name it. If you're shopping on Amazon.com, you're interacting in some way with machine and deep learning systems under the hood.
Now, Amazon has multiple pillars of strategies related to AI and machine learning. You guys use the technology, of course, extensively for all of our shopping experience and managing your warehouse and just internal operations and automation. There's another pillar that has to do with robotics and the work that you guys do with Echo and Alexa. And then there's another, the new pillar that you guys introduced, I guess about last year, was taking all of this technology that you guys have invented and putting it up on the cloud so that everybody, every developer, every startup company in the world, every enterprise in the world could benefit from these pre-trained networks of yours and create applications based on AI.
That's right. So the original goal with Amazon Web Services, the very, very first business case, was to be able to take technology that was only within reach of a very, very small number of very, very well-funded organizations and put that within reach of any developer anywhere. And you can see that that's been used now with millions of developers active on the platform every single month. And we're doing the exact same approach as we took with compute and enterprise data warehousing and applying it to deep learning and artificial intelligence, using computer vision models, speech systems, speech recognition, natural language understanding, and doing a lot of work in driving Apache MXNet forward for all developers. We've seen and been able to work together, our two teams, really to optimize MXNet for Volta. We couldn't be more excited. We've seen amazing performance improvements, both in training and inference. And we're really excited to be a launch partner for when Volta becomes available. And we'll make Volta available as the foundation for our next general purpose GPU instance at launch.
That's amazing. That's awesome. Thank you very much. I really appreciate the support.
Right, thanks.
Now, everybody in the audience probably wants to know the same thing I want to know. What's the funniest question that Alexa gets?
The funniest question that Alexa gets, you know what? It's almost always
PG, by the way.
It's actually almost always from kids. I bought a new Echo Dot. You can order it just by asking Alexa for it. It arrived. I took it out of the box, and my son was with me, and he said, "Hey, Dad, can I hold her?" Not can I hold it, but can I hold her? And the affinity that customers have for Alexa is really incredible and growing every day. We have a remarkable ecosystem both of devices from Amazon, third parties integrating Alexa into their own cars and refrigerators, and also more than 10,000 Alexa skills available on the platform today. So it's a bustling ecosystem which I encourage everyone to experiment with.
And so one more question that I'm dying to know about. You know, Amazon today has the world's largest scale of GPU cloud. And I remember Andy telling me that when you guys rolled out the GPU into the cloud, it was the fastest growing instance that Amazon ever had. And I guess my question is what did you guys see? How did you guys know that people want a GPU in the cloud, and why did you guys do it in the first place?
Yeah, I mean, it really came from customer feedback. About 90% of our roadmap at AWS is driven directly from what customers ask us for. And they were really asking for Nvidia chips available with utility pricing and availability. And so we made that available. We've been working together for years. Our most recent instance, the P2, is just growing like wildfire. It's being used extensively for deep learning in virtually every vertical. We see medical imaging, even in regulated workloads. One of your examples earlier, the FDA approved regulated workload of deep learning for medical imaging, all the way through to the best performing autonomous driving simulation, which is from a startup called Too Simple. They do everything from real-time per pixel object segmentation to centimeter accurate positioning of the car in three-dimensional space, all up and running on P2 using MXNet on AWS today.
That's amazing. Thank you very much,
Thanks.
Jeff. Thanks for all the support.
Cheers. Thank you.
Congratulations.
Thanks.
Amazing work at Amazon, revolutionizing computing as we know it, creating the future with cloud computing. The first thing I want to announce is our brand new DGX-1V. This has become the essential instrument of deep learning research. The work that they do, deep learning scientists that are so heavy, and building a supercomputer or a high-performance computing cluster takes a great deal of time. Integrating all the software into it to make it performant takes a great deal of time. And finding space for it takes a great deal of time. For many of them, they either aren't quite ready for the cloud, or would like to have the ability to burst into the cloud. And so we created for developers the DGX-1 supercomputing appliance dedicated to AI. With Volta, it has almost, I wish I just had 40 teraflops more, because it would have been wonderful to say. 960 tensor teraflops with 8 GPUs inside. It can now take What used to take 8 days on tight necks to train now literally takes 8 hours. What took a week now takes a shift. And it replaces 400 servers. I don't know if you know what 400 servers look like. It's basically a full aisle of servers. Today, DGX-1V. Yeah, is that beautiful? The DGX-1V with 8 Tesla Voltas. And call your operator because we're ready to take orders. You can order one today for $149,000. Come to Nvidia.com. Have your credit card ready. And we'll deliver it in Q3. Now, only for you in the room. Everybody who places orders now, I'll give you, because Volta is not quite ready to ship now, it'll ship very soon. It'll ship Q3 and DGXs and Q4 from OEMs all over the world. For anybody who places orders today, starting today, you'll get a free upgrade to Volta when it arrives in Q3. DGX-1V, $149,000, replaces 400 servers or approximately a couple of $1 million worth of equipment, and it comes out of the box, plug it in, and it go to work. Well, we've been asked so many times, would it be nice? I don't have a data center, and I don't have cooling. I'm a startup, and I've got 10 engineers. And what we need right now is to get working on deep learning. Could you please make us a small version of DGX? And so we thought, well, that's an interesting idea. So we prototyped up a few inside the company. And of course, putting that much computing power next to an engineer, you really, really have to keep it quiet. So we liquid cooled it. And it's whisper quiet. You can't hear it at all. And so we created it, and we can't make enough of it. Every single deep learning engineer in our company either has a DGX station or a DGX-1 or both. Every single one of the engineers. And so this is just an amazing, amazing success inside the company. And so I decided that we would make it and make it available to deep learning engineers all over the world. Ladies and gentlemen, the personal DGX, called the DGX Station. And for those deep learning engineers that just started the company and would like to get going quickly, this is one way they could do it. And when they're ready, burst it up into the cloud. For a simple $69,000, you have your own personal AI supercomputer. You can order it now, and we will deliver it in Q3. So place your order now. So that's one configuration of how Tesla gets used in a DGX station in DGX-1 for a personal AI supercomputer. The other way that we use it, of course, is putting it into the cloud. And one of the ways that we use it is putting it into a public cloud. When you put a service into a public cloud, GPUs are used in a whole lot of different ways. They might be used to train certain types of networks, and different types of networks like different type of computer configurations. They might use it to run molecular dynamics. They might use it to run, as Matt was saying earlier, a segmentation or maybe even a simulation or computer graphics in the cloud. And so we need this computer to be very adaptable. One of the things that we did was we partnered with Microsoft to create the industry's first industry standard hyperscale cloud graphics accelerator. Notice there's a computer, there's a 1U computer underneath the server. And there are these 4 cables that come out from the base computer into the HGX-1. And these cables are basically PCI Express. And it allows us to configure this server in 2 CPU and 8 GPUs, 2 CPUs and 4 GPUs, 1 CPU and 2 GPUs, and so that they could provision all kinds of different size services to the market. And of course, we still have the ability to virtualize the GPUs so that many instances can run on 1 GPU. This particular box is intended for the public cloud so that the versatility of service could expand the reach of the customer base. Whether you're using it for deep learning, or using it for graphics, or using it for CUDA HPC computation, HGX is really ideal. I'd love to have Jason Zander, who is the Vice President of Azure, come and join me. We've been partnered together for such a long time working on this. It's great to have you. Jason, welcome.
Thank you, Jensen. Appreciate it. Happy to be here.
You know, our companies work on, first of all, I'm really, really grateful that you're here. As you guys know, right now, simultaneously, Satya and Harry Shum, the CEO and CEO and the CTO of Microsoft, are up in Redmond doing almost exactly the same thing we are.
Our Build conference is today.
It's called Build. And so I'm really grateful that you took the time to come down here and spend it with us. We've been working with Microsoft for, gosh, 25 years.
Yep.
And we have all kinds of developments going on. Recently, we've been working on, of course, advancing deep learning for internal research. And very, very amazing. Well, first of all, Harry Shum, XD Huang are some of the world's pioneering AI researchers in speech. And the work that you guys did recently to achieve superhuman levels in speech recognition was a complete groundbreaking endeavor. Not only that, you guys were able to create natural language translation for real-time Cortana. So apparently Cortana now can understand 40 different languages. And of course, you guys had a great groundbreaking work with ResNet, developing a very, very deep, very sparse network that was very powerful and achieved superhuman levels. This AI laboratory inside Microsoft uses a framework that they call back in the good old days, they called it CNTK, and which has now become the cognitive toolkit. And tell me about the work that you guys do there, and how you guys are going to expose that to the rest of the world so that everybody else can have the benefits that.
Yeah, thank you. You know, AI is a clear part of what we're trying to do. We want to infuse AI across our entire platform. So we start off with the platform, our partnerships that we have, cognitive services and frameworks like Cognitive Toolkit, and now the Cognitive Toolkit used to be CNTK, but also into our applications, because we want users to be able to take advantage of that as well and make sure that's available to them. And so we've been doing AI for a good 20 years now, if you think back to things like search relevancy, all the way out to things like Kinect sensors on the Xbox, and most recently HoloLens and those environments. You mentioned the real-time speech translation, the Skype real-time translator. That's one of the most sophisticated language deep neural nets that are out there. It can take us hundreds of GPUs. We can spend an entire day running this thing through, but it's really cool because I can talk to someone in English and they can hear in Chinese and go back and forth, and you say lots of languages. Can't do that without the power of the cloud.
The Star Trek Universal Translator is going to happen.
It's awesome. It's finally here. Really excited.
And so I could just imagine, so that's right. So you guys are working on a HoloLens, and a HoloLens is, as you and I know, and it has real-time 3D reconstruction. It recognizes the 3D environment, and it augments computer graphics and register it perfectly inside reality, augments reality. And now, if you supplement that with the Cortana natural language translator, you're able to walk up to anybody from another country, and you could talk in your language, they could talk in their language, and the two of you could have a perfect conversation.
It's really cool. I mean, the idea that I can trap photons and do things with it before it hits my eyeball is pretty awesome. So that's another exactly great place where we're able to leverage the work that we've done together, because doing the API and algorithm validation on the back end for the HoloLens, also another thing we can use inside of the fleet. Combine that with real-time translation. Like you said, I can have this really cool interaction model that's there, and you can't do it without the deep partnership that we've had, already so far.
Nobody would have guessed that Microsoft would be one of the fastest growing cloud providers on the planet. And in the last several years, your Azure business has just been on fire. And you have had the support of Natya and everybody is behind your business, pushing Microsoft Azure into the world. And so tell me about some of the efforts there, and talk to me about some of the collaboration that we have, and how can we bring GPU computing to the world?
Yeah, and it's really exciting times for us. So we're on our second generation of GPUs inside of the fleet. We're the first to bring in M60s and the K80s. We've just announced the P40s and the P100s are coming. And then, of course, we really, really love the Volta work that's coming out. We want to make sure that goes out there as well. Look, my job is to make sure that both my internal folks inside of Microsoft developers, they use the Azure cloud in order to be able to do their training. Like the examples we just mentioned. And look, every time you come up with a new system that comes through, they want it tomorrow. tomorrow. And so our ability to come in and make sure that it's part of the training regime that we've got, it makes things go faster, like your benchmark showed. But then we also want to make sure that it's available to all of you. And we've done additional things. For example, our cognitive services we've had out. We've actually had it out for about 3 years now. We've been doing AI, speech, and text, and these APIs as part of the services on top of the Azure cloud. And we're bringing even more of those coming forward. In fact, we just announced the Azure Batch AI training service that's out there, which kind of, our history is a lot of developer stuff, right? We want to democratize that. And so we want, data scientists and basically developers that are working on models, let them concentrate on the models and the unique IP and value they add, and less on the plumbing. So you're going to see more and more of that come in through the system. We think it'll help accelerate some of the scenarios that you're showing.
Yeah.
It's really super exciting time.
Well, Satya is going to be super excited about the work that we're doing together. You guys announced yesterday the largest installation of GPU cloud that Azure's ever announced. And so I'm super excited about that. Thanks for your support, and thanks for your support with Volta.
Thank you so much.
All right,
Appreciate
thanks,
it.
Jason.
Thanks.
Jason Zander, Corporate Vice President of Microsoft. Let me talk about inferencing. So now we've created this network, and it's taken hours and hours of deep learning training on DGX1 or in the Amazon cloud or in the Azure cloud with all these GPUs. Now that you have this network is now ready to be deployed. And that network is still very computationally intensive, and we need to figure out a way to make that network run as fast as possible. There are two things that we are doing with Volta that is really, really special. The first, of course, is the Tensor Core that I mentioned earlier. It increases the throughput of training by a factor of 12, but it increases the throughput of inferencing by a factor of 6, and I'm going to show you the benefit of that. But the second thing is this. Whereas the frameworks are used for training the network, when you're done with it, it creates a graph, and that graph needs to be optimized and compiled for the processor that you're using. We call that Tensor RT. Tensor is basically a mathematical object. It's like a vector. It's a generalized vector containing a lot of multidimensional objects within it, and this tensor needs to run in real time, and it comes into our software in the form of graphs. And so the first thing that we have to do is we have to interpret from each one of the frameworks, parse and ingest from each one of the frameworks. The second thing we have to do is compile it, and the third, optimize it for each one of the targets. And each one of our GPUs has slightly different architectures. They have slightly different numerics precision, and we have to take advantage of each one of our GPUs. We call it Tensor RT, Tensor Runtime, Tensor RT, graph optimization for vertical and horizontal layer fusion. So if you take a look at this, this is basically a neural network. There's the convolution layer, the bias layer, the rectified linear unit layer, and basically the activation layer. And this is one particular network, a typical network. This, I believe, is AlexNet. What we do with it, the first thing that we do is combine the mathematics that otherwise would have to be done in sequence into one big blob. And so we turned a ReLU, a bias, and a one-by-one convolution into a one-by-one convolution bias ReLU. And so that mathematical block is replaced. So by analyzing the graph, we could figure out which one of the mathematical operations we could fuse together and replace with something much more efficient. The second thing we could do is we could recognize when different mathematical blocks share the same inputs. They have different outputs, but they share the same inputs. And that, again, is achieved through graph analytics. So we can walk through the graph, we can analyze the graph, and recognize these different opportunities, and simply remove them, okay, in this particular case, and share them. And then the third thing, of course, is compile it down to the precision of the target GPU. Now, this is the inferencing performance. Let me show you. Broadwell, this is the fastest CPU of today. Skylake is the next generation CPU. We haven't had a chance to benchmark it yet, and so we're giving it the full credit of what's possible. K80 is the GPU that we announced 5 years ago, okay? And the y-axis is images per second, how quickly it can do inferences in 1 second. Now, P100 is able to do 600 images per second. There are two important numbers. Not only is the throughput important, but the latency, how long it took you to do it. Not how many you can do, but how long it took you to do it. The latency is equally important, and the reason for that is because if you were talking to a neural net, if you were talking to Cortana, and you asked Cortana the question, you would like it to respond very quickly. in just a few milliseconds, And so the number of people who could speak to Cortana at the same time in the cloud is important because that has something to do with the capacity of the data center and the cost of the data center. The second thing is the latency of that performance is equally important, if not more important, and the reason for that is because that has something to do with the quality of service, okay? And so the purple line is latency, the green line is throughput. So P100 has the benefit of 600 images per second, and Skylake is about 300, the next generation Skylake, and both of them could do it in about 10 milliseconds. This is what Volta looks like. That is what we call a little bit faster. And so Volta is really groundbreaking work. Not only is Volta incredibly good at training, it is also incredibly good at inferencing for the very first time. We've not focused on inferencing in the past, and the reason for that is because the number of networks that are being created was still rather limited. But now, internet service providers and cloud service providers and startup companies and enterprises all over the world are starting to move deep learning into production. They need an inferencing pipeline. And so Volta, TensorRT, ideal for inferencing. The way that we deploy it into a server is also unique. And the reason for that is because these scale-out servers, gosh, Sandy, why do you keep standing over there? Why do I keep going over there? Sandy, stage manager, she's fantastic. Ladies and gentlemen, this is Tesla for hyperscale scale-out. Look how small it is. Look at this thing. It's like a CD case, but more beautiful. And it's gold. It might actually be real gold. Okay, so Tesla V100. And this is what we call the PCI Express FHHL, the sexiest name ever. Full height, half length. Who does that? I couldn't rename it. It was too late. The industry took it and ran with it. Full height, half length. Try to say that without chapstick. Okay, so this is, and not only that, it runs at 150 watts. 150 watts. 150 watts. And it fits into these commodity inferencing servers. And here's the, thank you, Sandy. This is the case I want to make. This is the reason why people are talking about accelerators for data centers. I like to make the case for accelerators. Here's how it works. And so this is what 500 nodes look like. Earlier I said 400 nodes. This is what 500 nodes looks like. 500 nodes is basically this entire row of servers. Okay? It's an entire row of servers, 500 nodes. Well, basically this 500 nodes can support 300,000 inferences per second. 300,000 7-millisecond inferences per second, which means if 300,000 people were connected into this data center and did a query or okay something or look for something, and those inference networks were activated, we could support 300,000 people in this rack. 300,000 inferences basically translates to about 1,000 CPUs, because as you saw earlier, the state-of-the-art CPU, the one that hasn't been announced yet, is 300 inferences per second. And so 1,000 CPUs basically translates into 2 nodes, because each one of those little nodes, long nodes, has 2 CPUs inside. If we added all of that together at $3,000 per node, and remember, you have to buy the node, there's the interconnect, okay, and then there's all of the power that goes along with it. Power and cooling represents about 40% of a data center. But let's ignore all of that for a second. And so 500 nodes translates to basically $1.5 million, not to include all the cables and all the power delivery and the cooling, et cetera. And it consumes 500 watts each, so 250,000 watts, 250 kilowatts. Well, if we used a a relatively conservative number of about 15x reduction, that basically translates to 33 nodes of this. That translates to 33 nodes. That's the savings. Instead of 500 nodes that occupies an entire row, you can replace it with 33 nodes, or you could increase the throughput of your data center by 15 times and not have to build more data centers as AI workloads floods into hyperscale data centers. This is one of the most important reasons why people ask us about FPGAs and accelerators and so on and so forth, and we decided, why not make Volta the best inferencing machine that can possibly be made? And as a result, the results are incredible amounts of savings. Okay? So Tesla Volta for inferencing. Let me show you one more thing that's really super important. We've been working on all of these stacks, and the stacks are so complicated. You got a whole bunch of GPUs, whole bunch of drivers, whole bunch of systems, whole bunch of middleware, all these different numerics, all these different frameworks, and there's so many frameworks, there's so many GPUs, there's so many versions of software. The ability for the industry to maintain all of this complicated stack of software, arguably the most complex stack of software the world's ever seen, is really, really, really difficult. And in fact, when you read the forums, it is such a pain. And for many deep learning engineers, it takes anywhere from a solid day to a couple of weeks to sometimes never achieving building a computer that can do deep learning. And so what we decided to do was take this incredibly complicated stack and containerized it. We containerized it, and we dedicated ourselves to containerize every single framework and every single version of software that we know. And then once we containerize it, we're going to create a cloud registry for it. Okay? We're going to create a cloud registry for it. We're going to take all these containers, we're going to create a cloud registry for it, and here's how it works. So whenever you're ready and you have a Titan X, and you're one of the several 100,000 deep learning engineers in the world that has Titan X's, and you bought a Titan X, you don't want to build your own deep learning machine, you simply go to a website, type in your email address, register for this, you download the container of your choice. You download the container of your choice. That entire stack of software is fully optimized. It's fully integrated. It's containerized. It's virtualized. We download that into your machine. You start doing deep learning basically in a few minutes. There's no configuration, there's no building, there's no worrying about different versions. It's configured basically in just a few minutes. Uses a container called the NV Docker, and we create a registry for it. We support every single framework. Then the next thing is, once you start using, you used to use the platform, you start to realize that, gosh, I sure would love to have a lot more performance. And nothing would give me more joy than to tap into the 10,000 GPUs that are in the cloud. With just a click, you create an instance up there, we download the container up there, and we burst your workload into the cloud. Okay? So this is really the first hybrid deep learning cloud computing platform. And what we provide is just a registry. We provide the registry, the cloud computing platforms provide all of the cloud computing infrastructure, and we maintain the software, optimize the software for as long as we shall live. Let's take a look at it. Phil.
Yes, so the NVIDIA GPU Cloud provides multiple interfaces for developers and users to run deep learning. I'm going to focus today on the web application running in a browser. So we log in. And this is where you create your deep learning job. And there's just 3 steps. First, we select where we're going to run our deep learning workload. We call this the accelerated computing environment. You can pick from cloud, or your own DGX-1 cluster, or a DGX station, or a Titan PC. Today we're going to focus on cloud. And you can see the options you have here include the Microsoft Azure, Amazon AWS, and the NVIDIA Saturn V. This is the DGX supercomputer we built for internal development. I'm going to select an 8 GPU node because I'm going to run a fairly heavy ResNet training session. In the second step, you attach a data set or multiple data sets to your job. Here, and you get a choice between the existing data sets that you've already uploaded, or you can create and upload a new data set. I'm going to go with the ImageNet data set. And this particular data set has both training and validation samples in it, so I only need one data set for this run. Next, we select the framework in a container, as Jensen was just describing. All of the different frameworks are provided, fully optimized, and optimized for scale out to multi-GPU, so ideal for our 8 GPU run here. I'm going to take PyTorch, and I'm going to take the latest release. You notice the numbered releases. We optimize, update each of these frameworks every month. So at this point, my job spec is complete. I'm ready to go. But I want to notice that we echo out the command line that's equivalent to this web application run so that a developer can copy and paste this into a script and run it from one of our other interfaces, such as our command line interface. So now I start the job, and that takes us to the dashboard. This is the control center for the Nvidia GPU cloud. You can see jobs that are running and queued and your recent history. And the list of jobs covers all of the accelerated computing environments that you've been running in. And you see the job at the top is the one we just created, the ImageNet 256. It's already running. And you can click on any job to look at telemetry. There's a job here on 4 GPUs I started a little while ago. It's also ResNet on PyTorch. And you can see we're keeping these GPUs running flat out as we run this training session.
That's great. Thank you. Good job, Phil. And that's it. That's the GPU. That's the GPU cloud, the Nvidia GPU cloud. And it's a containerized system. It's a registry in the cloud, supports every single framework. And the thing that we will do is we will support these frameworks and every single one of the versions and every single one of the permutations of them on every single one of our GPUs for as long as we shall live. And that's something we do for accelerated computing for each one of the markets that we serve. It's going to be available beta in July. The Nvidia GPU cloud platform. Okay? For all of you who are anxious to burst into the cloud, this is the way to do it. All right, so let me summarize quickly on accelerated computing. If you take a look at some of the results that I've shown you, it is very, very clear that as Moore's Law comes to an end, that accelerated computing is really a wonderful path forward. And it's a wonderful path forward because of the architecture, because of the system software stack, and because of the domains that we've selected, and the fact that we work across each one of the application's middleware and the architecture in an iterative basis. And over time, you can see that the results continue to compound. On the left is Amber Performance Molecular Dynamics. On the right is GoogleNet Deep Learning. In both of those examples, we continue to advance. I want to now talk about AI at the edge. I've got some delightful things I want to share with you. I'm going to go quickly. You guys know that we're really dedicated to the automotive industry. And the reason for that is we believe that everything that's going to move someday will be augmented by autonomy. Everything that's going to move someday is going to be augmented by autonomy. We're enjoying, as you know, the Amazon effect. As we every single day buy things, don't forget, we used to drive to the store to pick up things, but now we expect the things to come to us. The number of truck drivers, the number of transportation professionals can't keep up with the Amazon effect. And so we have to find a way to automate as much of that entire path as possible. Augment it, take pressure off of the drivers. The number of truck drivers, for example, in many countries is short by about 50%. And so we need to find a way to automate some of this so that we can keep up with the Amazon effect. Not to mention, society could be much, much more beautiful, and our environments could be much more beautiful if we didn't have so many parked cars. Very few of us would remember that for every car that we own, there's actually 3 parking spaces created for us, not even including the one we already own. And so there are 800 million parking spots in America. There's only 250 million cars. And it makes a lot of sense because we just never know when we need it. Okay, so I think autonomous vehicles, transportation, will be augmented by autonomy in the near future. We've created a platform we call the Nvidia Drive. And basically, it's a roadmap. It's an architecture that spans level 2 to level 5, from augmented driving all the way up to completely driverless systems. We created a full stack. We dedicated ourselves to go solve the self-driving car problem and create the software stack, but open up the software stack. To create the software stack, understand the problem deeply, but to open it up. And keep it open so that hundreds of people can use it. We now have 200 developers around the world using Drive PX. They're startups, they're shuttle companies, they're car companies, they're trucking companies. We have wonderful partners in Bosch, the largest tier 1 in the world, ZF, the largest trucking tier 1 in the world, PACCAR trucking company, all the startup companies that I mentioned earlier today. It's all possible because the Drive platform is open. And it's open on so many different levels, you can intercept it at any level that you desire. Let me show you a couple of videos of what it can do, and then I got a big announcement I'd like to share with you. And so the first thing is this. The first thing I'm going to show you is mapping to driving. Basically how the car figures out where it is in the world and localize within it and detect everything that's around it and drive. The second thing that I want to show you is how we use AI not just for driving, but also to be essentially a virtual co-pilot. And third, this is a phrase that Gil Pratt at Toyota created that I really, really love, and it's called a guardian angel. Even when you're not driving, even when the car's not driving for you, even when the car's not driving for you, it should be watching out for you. And so the AI is on all the time, even if it's not in autonomous vehicle mode, it should be watching out for you. So let me show you a couple of videos. The first one is mapping to driving. And so in this particular case, the first thing that's happening is we're using the LiDAR. We have a LiDAR mapping car, and we're trying to detect everything that's around us, whether it's the lanes, the vertical poles. We're trying to create essentially an HD map of the structures in the world that we ought to use to localize ourselves later. Okay, so we detect all the road features. We construct the HD map. There are amazing companies who are doing this. We create the middleware, and there's a great company called DeepMap who does this, and of course TomTom does this, Here does this. Mapping company, we're partnering with mapping companies all over the world, and now we put that into our car, and it's in autopilot mode. Notice it's detecting the cars around it, it's detecting the lanes, detecting all the signs, and now you have confidence that the BB-8 is driving safely in the road, okay? And the next one is Copilot. This is our own Janine.
I can now drive you to work based on mapping previous drives. Shall I engage autopilot?
Oh, sure.
Autopilot engaged. Driving to work.
Janine is in our marketing department, and she's also one of our test drivers. She's very, very brave. And so, beautiful and brave. All right, so she has the benefit of a co-pilot there, and basically what's happening is this. Of course, we're not going to have the whole world mapped. And we're going to map the world as fast as we can, and wherever it is mapped, the car should know. And it just lets her know that, hey, gosh, I could drive the car for you now. Would you like me to take over? And the next, let me show you Guardian Angel. There we go, green light, time to go. Whoop.
Cross traffic danger.
Maybe not.
All clear.
Disaster averted. Okay? And so this is possible because the car sees everything around it all the time. Well, we have partners, as I mentioned, 200 partners around the world. They're startups, they're shuttle companies, they're even Airbus creating a self-flying plane that they would like to make available in the year 2020. It's a VTOL, takes off by itself. It occupies the space of 2 parking lots, and it's for 2 passengers, and it'll go 70 miles. I can't wait for this. This is incredible. And so Airbus is creating an autonomous airplane. They're a Dutch company using our platform for autonomous ships. There are companies who are using our platform for autonomous pizza delivery. And so keeping this open, creating an open platform, AI computer that everybody can use has proven to be incredible. Well, today I'm just incredibly honored to announce that Toyota has selected Nvidia Drive PX for their autonomous vehicles. As you know, Toyota is one of the largest companies in the world. I believe they're the 9th largest company in the world. They have 350,000 employees. This is a company that is legend in so many different ways. So much of modern management has come from Toyota. Kaizen, continuous improvement. Genji Genbutsu. I bet you guys didn't know about that one. Go to the source, see it yourself before you come up with a solution. Just-in-time manufacturing. The pull model of manufacturing, not push. So many of modern management systems were invented by this company. It's an incredible company. They dedicate themselves to the highest level of safety. So they're working with us, and the two engineering teams are now working incredibly hard together to create their autonomous vehicle car. And we'd like to finish it and put it on the road in the next few years. We would also have a mutual goal, a combined goal of achieving zero fatality someday. And so this is going to be their architecture for their future production cars. I'm super excited about that. Ladies and gentlemen, Toyota on Drive PX. The processor inside this Toyota machine autonomous machine will be the Xavier. Some of the things that's really cool about this is this. A lot of people are surprised. How is it possible you guys could put 30 trillion deep learning operations in 30 watts? Well, the reason for that is this. And this is a question that's come up a lot recently about accelerators and TPUs and FPGAs. Basically, the way you think about these processors, the CPU and the FPGAs are general purpose. They could almost do anything. You can make a CPU, you could write any software for it. You could use an FPGA to do any video decoder, Ethernet chip. You could make it do almost anything. The flexibility of these two architectures comes with it the cost of efficiency. The cost of efficiency. The next three processors, two CUDA GPUs, one is Pascal, one is Volta, and the last one, the one on the bottom, is called a DLA. The DLA, Deep Learning Accelerator, what some people would call, for example, a TPU. They are specialized in their domains, and so therefore, they tend to be much more energy efficient, they much more performant within any constraint, I've already talked about how CUDA has been improved with the Tensor Core, and so Pascal's level of deep learning capability, although great, is now enhanced by Volta. You could take that even further. You could create a custom ASIC with, we call the DLA, and you can improve the energy efficiency by another third. Okay, you can improve it by another third. And so this basically gives you a landscape of all the different processors in the world. For our data center products, we need it to be flexible. We need to be able to run almost any network that comes our way. And so the flexibility of CUDA is too valuable for general purpose computing platforms, for data center platforms. However, in the case of Xavier, we've done something very special. What we've done is we've created a processor out of these three. In order to drive, you still need to localize, you need to reason about where you're going, you need to plan, and the planning process is highly parallel and requires 32-bit floating point processing. And so we decided that we would use CUDA for that. We also know that there's all kinds of interesting networks that we're about to deploy, not just computer vision object detection networks, but much more sophisticated networks for the future, and we need programmability for that. And so Xavier includes the CPU's single-threaded performance capability, CUDA's flexible parallel acceleration capability, and it also includes a deep learning accelerator that provides for specialized functions in computer vision. Well, the thing that's really great about this is now we have an architecture that is both programmable, super energy efficient, robust for all kinds of networks that we can come our way, can run the entire software stack of self-driving cars. And as we were thinking about building this, we realized that there are so many companies in the world who would value having the ability to create a deep learning accelerator. We understand this space so well because we understand the entire pipeline. We understand the entire pipeline from the beginning of the creation of the network all the way to deploying it into any environment. We understand and we have the software stack across the board. And so what we decided to do was realize that, gosh, it's so incredibly hard to put all this stuff together. Why don't we accelerate the adoption, democratize deep learning, lower the barrier of entry for every single of the trillion devices in the world that someday that will use deep learning. We're not going to build them all. We're not going to build them all. However, we would like to see adoption to accelerate for all of them. And so, ladies and gentlemen, today we're going to open source the Xavier DLA. The best engineers in the world are working on the deep learning accelerator. We're going to take this accelerator, what some people call TPU, and we're going to open source it. And you can continue to follow our instruction set, or you could decide to change it. If you adopt ours, we'll continue to support it with software. If you decide to change it, it's no big deal either. Okay, it's completely open source. We're going to early access it in July, and we'll have general access in September. Our goal is proliferated. Robots. Robots is the ultimate version of artificial intelligence. The robot is interesting, and it's going to revolutionize a whole slew of new industries, from manufacturing to healthcare. We know that robotic surgery is now able to perform surgeries that we simply can't imagine. However, don't forget that in the future, we're going to have cybernetics. We're going to have robots that are connected to parts of our body. We're going to have little tiny robots that take care of various tasks. Robots, unfortunately, are incredibly hard to do. And the reason for that is because it has to sense the world, which we know how to do now. It has to learn from it and plan and take action, but it has to interact with the world. In the case of a self-driving car, our fundamental goal is collision avoidance. That is a specific objective. In the case of a robot, collision detection is essential. Your goal is to connect, your goal is to collide. How you collide is incredibly difficult to do. There's so many degrees of freedom in all of the joints and fingers and elbows and wrists and torsos of a kinetic object that training it is incredibly difficult. And so recently, some breakthroughs have happened. This is Ada at the Berkeley AI Laboratory, and they've taught Ada how to play hockey. And that right there is probably one of the world's finest AI researchers, and that's what he does for a living. And that's Ada learning repeatedly using reinforcement learning how to play hockey. Now, it turns out that hockey is not too bad. First of all, convincing people to do that for all of your robots as you train it is probably difficult to do. However, remember, that's just hockey. What if we wanted to lift a car? What if we wanted to open a door? What if we wanted to cooperate with a doctor to do surgery? There is no way to have it learn this way, repeatedly in the physical world. And so the answer is this. It turns out we need to create an alternative universe. We need to create an alternate universe. This alternate universe has to obey the laws of physics. In the sense that there's collision detection, it obeys the laws of physics and gravity if you choose. If you choose. It has to be visually photorealistic. It has to look like the world, or these robots can't learn within it. It has to look like the world, it has to sound like the world, it has to behave like the world, and it has to have the ability to learn inside this alternative universe. We have to be inside it as well, so that we could teach it using imitation learning, using all kinds of new deep learning techniques. So it has to be a virtual environment that we could be part of as well. This alternative universe that is visually real, that is physically real, has to have one additional characteristic. It should not follow the laws of time. The only thing that we expected to do is to be hyperspaced. We would need it to train in warp speed. And the reason for that is because there's no reason for us to have to wait around for IDA to learn how to play hockey in the physical world in real time. And so we created a new tool. It's a new world. It's a new simulator we call Isaac. Isaac is named after the two Isaacs. Isaac Newton for physics and Isaac Asimov of AI. We brought the two Isaacs together into this new world we call Isaac. Isaac has the input of environments and robots. So we can put virtual sensors of the robot, we put the virtual actuators and the virtual effectors of the robot into it, and it's connected to OpenAI's OpenAI Gym, where all the reinforcement learnings and all the interesting algorithms that could be applied. We would simulate in this environment and run it on top of any Nvidia GPUs, and inside that computer is a virtual brain. And when we're done with it, we literally take that virtual brain and put it into a real robot. And this robot wakes up almost as if it was born to know this world. And then the last little bit of domain adaptation that it does is done in the physical world. And so when a robot turns on, it has already been pre-trained, if you will. And it would be pre-trained in the Isaac world. And we, as a company, have the unique capability to bring this capability together. We know how to do physics in super real time. We know how to do amazing computer graphics. We know how to do AI. And so we decided to integrate it all into one thing we call Isaac. So ladies and gentlemen, let's take a look at it. This is Isaac. We import mechanical or the environment into it, and we could train Isaac. Now, in this particular case, Isaac has been trained. And so notice, when Mike moves the puck, when it moves the net, Isaac somehow figures it out. Oh! Now, this all looks wonderful. Okay, this is all in computer graphics. Now, one of the things that we could do is, of course, we could replicate a whole bunch of Isaacs and have them all learn. And then we take the smartest one. And we take the brain out of that smartest one and we put it in everybody else's brain. And then we say, okay, now start again. And then we figure out which one's the smartest one. And we take that brain, we put it into everybody else's, and we say, start again. And so as a result, we could accelerate the time to learning. Look at all these Isaacs. They're all trying to figure it out. They're all trying to figure it out. And so that's great. Let's take a look at some of the clips from when they were learning. It's got to figure out where the puck is. It's got to see the puck, figure it out. It's got to figure out how hard to hit it. It's got to figure out where to hit it. That's incredible. Now, guys, ladies and gentlemen, Isaac. Well, look, if it can learn how to play hockey, it can surely learn how to play golf. And so here's Isaac learning how to putt. And so let's do it. There's Isaac. Reads the green. Nice. Now, remember this. No programming was done. Isaac just sat there and tried until it figured out how to putt. Okay, not strong enough. Well, let's get, really? Oh, no way. All right, let's give, I was going to say, let's give Isaac something hard to do. Let's move. Oh, here it comes. All right. Okay, good job. Thank you very much. Ladies and gentlemen, Isaac. So the next time you guys see Isaac, I hope that Isaac is standing in the middle of a sand bunker, and we'll teach you how to chip out and see if we can sink it. Okay, so Isaac, this is a robotics simulator, the next stage of AI, where you have to sense the world, figure out what you learn from the world, and plan about what you're going to do, take action, sense the results of your action, and you go around in that loop. And we created a simulator that makes it possible for robots to learn inside this virtual world, this alternative universe. And hopefully, as we put this out there, there'll be all kinds of robots that are going to be created, and they'll use reinforcement learning and transfer learning and imitation learning and other forms of learning in order to program these very sophisticated robots. That's it. That was what we talked about today. We talked about two things. We talked about the fact that accelerated computing is really coming to the fore. This is the rise of accelerated computing. Our GPU computing platform has been adopted by high-performance computing scientists all over the world. And recently, with the advent of deep learning and the breakthroughs there, we're now seeing a new era in computing we call the era of AI. Volta is the next generation, next giant leap into that new world. We also introduced several things with Volta. One is a brand new instruction set we call the Tensor Core. Second, a full compiler and optimizer for inferencing we call Tensor RT. Between Tensor Core and Tensor RT, not only do we accelerate deep learning, but we also make it possible for hyperscale data centers to deploy deep learning broadly into their data centers without having to build more and more and more data centers. We can save 15 times the cost of deploying deep learning into the world. We introduced DGX-1 and DGX-1 Station. Both of them are open for orders now. We also have the support of every single cloud computing partner in the world. And so you can find the Nvidia GPUs with all of our software on Alibaba and Amazon and Baidu and Facebook and Google and Microsoft and Tencent. Every single cloud will have this one standard architecture. One of the things that we've done is introduce this idea of a containerized software stack that allows you to use one software stack without having to optimize your computer from premise to cloud. And this way, when you're ready to burst into the cloud, that software stack is already in the cloud registry, it's all fully optimized, and you don't have to reconfigure it. We also announced that we would like to expand the reach of deep learning, to proliferate this capability, to democratize the ability for every single IoT device around the planet, the trillions of them that are going to be able to use deep learning in the future, to be able to access a world-class design. We're going to open source the Xavier DLA design. We're going to continue to advance it, continue to improve it, and people who use it will continue to gain the benefits of it. We also announced two other things. Toyota has now announced their support and creation of their future autonomous vehicles based on the Nvidia Drive PX platform. And then lastly, we announced the first alternate reality virtual robot simulator so that we can hopefully work together to bring the future of artificial intelligence and robotics to the world. That's all I have today. Thank you guys very much for coming. Have a great GTC. It's great seeing all of you.